Hi there, welcome back. Welcome back to a more tanned presenter. I've just been in Porto Santo, the island of Porto Santo, for a few days. It's basically one big beach. It's amazing. And that's where a lot of us Madeirans sort of get in the car, jump on the ferry and cross the, 20 nautical miles or something. It's literally, 2.5 hours away. And that's where I've been. That's why there was no video the weekend. Anyway, I have a new project, and this is actually something I've been meaning to do for some time. I have another project from PCBWay. They are sponsoring this video. I want to thank them for it. This is a new board for a project I've wanted to do after I did that last LPAD project, which raised quite a few comments or questions in the comments. One of them was, why don't I use more precise resistor values? Well, yeah, you can. In fact, if you allow for three parallel resistors, you can practically get, within 0.1% of the theoretical values that you need for those attenuators. If you want to go and get practical, then even one resistor will do most of the time. I have done it with two. But what I want to do is this. I use this signal generator when I do the alignment of any FM on my radios. This is from ELV. It produces a stereo FM signal, and it goes from 88 to 108, I think it is. Yep. And so it allows me to do the alignment on those radios without needing one of those massive HP ones. The problem with this, as I mentioned before, is that it does have a fairly hot signal. And when you feed that into the 75 ohm input or whatever of a receiver, it's a blaring hot signal. So you can use attenuators that you plug onto the top here. And I've got quite a few. But I wanted something a little bit more simple to use. So I built this guy. And this guy allows me to, 10 dB attenuation, 20 dB, 20 dB. So I can sum those. That's up to 50 dB of attenuation. It also has an LPAD, which is a converter, an impedance converter from 75 ohms, which is what this system uses, to 300 ohms, which is what I normally require in the tube radios. They use the normal sort of dipole at the back. That is sort of accepted to be 300 ohms. I'm not sure how accurate that is, but that's the idea. This was built. However, recently I needed an attenuation for RF for 75 ohms. And of course I couldn't get it on here because this thing is only at 300 ohms output. It's fixed, okay? Some of you had mentioned that I should have put a switch where I switch between 75 ohms, leave it at 75 ohms all the way through, or 300 ohms. And that makes perfect sense. The other thing I wanted to do was to do a little bit more screening because, at 100 megahertz, your interstage interference starts becoming, valid. Measurable. So I wanted to put some more screening on. So I decided to do a completely new project. It's going to be through hole, all right? It's through hole, and it's going to have 10 dB, 20 dB, 20 dB, or whatever you want to put on here, because all you need to do is go to the online calculator and measure or calculate the values of two resistors, and you can make this whatever attenuation you want, okay? And then I will still have the option of the 75 ohms or 300 ohms switch for the output impedance. So I'll be able to use this on more bigger variety of equipment. And it's all through hole, as I mentioned, so it's going to be in a bigger box. So let me show you first what I've received. And here's the box from PCBWay. Let's see what we've got in here. We've got their 7th anniversary stickers, another pen, and the boards. I've already cut this. I've got 5 boards, and this thing is like $5. So once again, they are sponsoring this video, and I am going to put up this project as a shared project on their website, and this is what this thing looks like. And why do I have these funny things here, and why do I have those funny things there? Well, what I wanted to do, this thing is a break-off, okay? And then the idea is that because this is double-sided and all it is copper, And I am able now to solder that on there, if you can see what I mean, so that I can create a shield between the components on that side and the components on this side. Now obviously I trim this, just trim that off. Now I've got three of them, so one there, and one there. I'm not sure just how effective that'll be, but it'll certainly be better than nothing. But the other thing I wanted to do is to sort of experiment to see how you allow for a visible copper track or solderable track on there, and it seems to have worked very well. This is double-sided, so I've got a lot of ground planes on here. I'll show you the schematic and the board in a minute, or the drawing in a minute. And this is the other side. Now the way this is going to work is the components are going to go on this side. The switches are all double pole, double throw, and they are the proper switches, but I'm not putting them on here. I'm putting them on the other side. It'll be held onto the enclosure with these nuts, and that'll be sticking out the top. And we'll have these dividers in here. And the enclosure that I've chosen is this guy here. I think this one's from Banzai Music in Germany, but I think it's sort of a standard Hammond box. This thing is, 11 centimeters by 6 centimeters. The idea is that you get a box or an enclosure that can fit this board in there, obviously with those things broken off. And the enclosure should then let you do that. And it should also have a bit of space on there and on there. On the one side, probably on both sides, I'm going to put BNCs. So you want some space to be able to put the BNCs in there. But yeah, let me show you the schematic and what changes I've made. Not much is different. You've got the input and output. You've got those double pole, double throw switches over there. Signal comes in. If you want to bypass it, you just flick the switch up and the signal goes around here. So there's no attenuation. It passes on to the next one. You can do the same. Next one, same. So you can then choose which of these to flick on or down. You can do all of them, none of them, or any of them. So if you flick this down, what this meets is a series resistor, a shunt resistor, and a series resistor. This is called the series in, that is series out, and that's the shunt. And in this case, I've left space on the board for 2 resistors per resistor, so you can use parallel combinations to get closer to the ideal value, and we'll talk about that in a second. And in some cases I only use one. For example, this one's only got a 39 ohm and that's not connected, but the space on the board is there as well. So this will be the 10 dB one. That'll be 20 dB, and the resistor values obviously are different. Everything's referenced to ground. 20 dB, and then here we have that 75 ohm to 300 ohm switcher. If I leave it in the up position, then the signal comes in here. It's all 75 ohms up to here. Signal comes in here and goes up and across and down and out. So this is 75 ohm out. If I switch down, then what I get is I'm getting a 0 series resistor in here. I've got a shunt resistor and a series out. Again, a combination of resistors to make up the values that I'll show you in a second. So I will then have a signal coming out here that is sort of optimized for 300 ohm instead of 75 ohm output. And it'll also have a 11.44 dB attenuation. You can't get away from this. That's the minimum attenuation that you can get, okay, in this type of circuit. I'm sure there are others you can do better. This one, just resistors, this is what I can get. And I can switch it in as well. So I'm going to have an enclosure with 4 switches, 10 dB, 20 dB, 20 dB, and the 75 to 300 ohm selector. 2 BNCs, one in, one out, and that's basically it. It's very, very simple. If we look at the board, the input comes in here. There's the ground and input. There's the output and ground, and then we've got those resistor networks. This is the 10 dB one. This is 20 dB, 20 dB, and this is our selector. And between here, connected to ground, is this, call it a big pad, solder pad, which is basically what it is. It's defined as a solder pad connected to ground. And it's connected to the ground because this whole thing is a ground plane on the one side and on the other side. And then what I've done is I've gone and done these as well. And these 3 also have this pad here. And these things will fit. I'll break them off there, you break it off there, break it off there, and you can solder this vertically on here to separate the various sections. I think it'll make a difference. I'm not sure how much. I'm not even sure that I can really measure it or even want to. But yeah, it makes me feel good. The other thing is the ground planes. I've tried to put in as many vias between the one side and the other, because the other side's also got a ground pad. And that's basically it. And when we look at the 3D rendering of this, it actually looks exactly the way it came out, which is fantastic. This is what I wanted. This is what I got. Once again, shout out to PCBWay. They've done a great job again. They've made me look good. Okay, let's have a look at the values. What I'm using here is called the matching T-attenuator calculator. It's called an ALPad as well. This is the single-ended one. You can do it in balanced. I'm not too worried about balanced because the signal generator that I'm using is actually battery powered. I suppose you could go to the other extreme, but if you do it balanced, you've got a problem with the switching. And the beauty of this is that the switching is easy, because if you put a switch from here and you can go straight across the top, this entire circuit disappears. But the way they calculate this is you've got a series in, a series out, and a shunt. Those are 3 resistors. Now, this resistor and that resistor, if the in impedance and the out impedance is the same, these two are the same, okay? And the way you calculate that is, for example, if you have 75 ohms input impedance, 75 ohms output impedance, and 10 dB attenuation, I go down here and calculate, and it gives me the values here, 38.962 ohms, 38.962 ohms. So that's that resistor and that resistor. And then the shunt resistor is 52.7, which is that guy there. If I make that 20 dB and hit calculate, I get a 61.364 ohms on the series in, the same for series out, and 15.152 for the shunt. Now, the last one is where I want to get this impedance matching. I've got 75 in, 300 out, and as I've done before, I'm putting nothing there, and it's going to tell me something. It's going to tell me, there we go. If I put that as 0, it says the minimum impedance to achieve impedance match is 11.44. So I will put in 11.44 here, hit calculate, and it tells me that I need 0.009 ohms on R1, which is basically a short circuit, so no resistor, just a wire. 259.808 on this guy there, and 86.59 on that guy there. And obviously these resistance values aren't ideal, but I did a little calculation, little spreadsheet here, and that's the result. We've got the series in. This is for 10 dB, 75 to 75. Remember, it stays at 75 ohms all the way through there until the end. Series out and the shunt. Series in for 20 dB, series out and shunt. And then the series in for 11 dB, I put that 11, it's 11.44 or something, for the 75 to 300 ohm converter, in, out, and shunt. Okay, so if we look at this, these are the ideal values I get from that from the calculator. And then I've tried various resistors here. And I've put in, for example, in this case, a 39 ohm resistor, nothing on there, in other words, infinite on there. The result is just 39, and the difference, or the error, between 39 achieved here and the optimum is 0.1%. Same with this one. The 52.7, I've worked out, you know, this is good enough. 56 and 820 comes to 52.4 instead of 52.7. That's 0.5% below. Very good. The 20 dB one I used in the previous experiment. I tried 120 and 120 and I got 60. Somebody mentioned this. It actually works out much, much better. 68 and 680. That comes out at 0.74% at 61.82, 818 ohms. Same for this one. And then the 15 ohm, I just use 15 ohm. You can also use 18 and 100, I think it is. That comes out at 15.2 something. But this is good enough for me. The converter, the impedance converter with attenuation, this is the ideal value 0.009 ohms. To me, that's 0 ohms. And this 259.808 I get by putting 270 and 6800. That is damn close. That is very close. And the 11 dB, or rather the shunt one, 86.59, 106.80 comes out at 87.17, which is 0.68. So I've got my values and I'm happy with this result. You can make these whatever attenuation you want. You just go back to that calculator and you put in, let's say you've got 75 to 75 and you want 24 dB. Calculate. There are your values, 66 and 9.5. You want 36 dB? Calculate. Starting to get small, 72.6 ohms and 2.3 ohms. You want 3 dB. You see what I'm getting at, right? You just basically decide what attenuation you want. The circuit will accommodate this situation, or I should say this situation, and you literally put in the resistor values that you need for the particular attenuation values. That there will be wrong. That will no longer be 10, 20, 20, but hey, a little Sharpie, write down whatever you like. And really what counts is what you put on the outside of the enclosure anyway. So yeah, I'm ready to build this. Let's see what we've got. Okay, let's see what we've got here. We've got the board. It's pretty clean. You can actually just file a little bit there where I disconnected those shields. So my board is ready. My switches are ready. Double pole, double throw. And I've got a lot of resistors from Mouser. Yeah, we do get Mouser in Madeira. I think it comes through Spain, I'm not sure. But it takes quite a while, which is why these projects sometimes drag on for a while. And I've got the enclosure here. Everything's set. The first thing I'm going to do is I'm going to actually decide where this thing's going to go. And to do that, I need to get the BNC sockets. And it does look like those will fit. It'll allow the board to slide through. So I'm going to put this thing slap bang in the middle. Here we go. I've got the same distance there as I have there. And now I can decide where I want to put this on that axis. I think I'm going to move it down a bit more because these switches are not in the middle of the board. So I want them as close to the middle as possible. I think that'll do. And what I'm going to do is I'm going to mark these points over here, draw a line, and then I'm going to find the center of that, draw a line, and I'll have the points connected for those holes for the switches. Let me do that. All right, that's done. I'm not going to drill it yet because I can always then check once I've done the board. Now, I'm not going to go through the whole soldering exercise and showing you how I do that. I'm just going to get hold of my board, populate it as per the schematic. You've all seen that, you've all done that. And I'll show you when we get near the end. See you in a little bit. Okay, folks, here we go. It is done. Now, I've managed to solder those panels, those shields. I think I've got quite a good joint there. Everything is ground, including the shields, the two sides on the shields, and there are vias between them. So basically I have separated that section from that section and so on. And now when the top goes on, which is also aluminium, we get quite a good fit, and this shield goes quite close up to the lid. So I think we've got some pretty good shielding on there. Not sure just how good that's going to be, but here we are. I've got the two BNCs in there. I did not solder them directly to the board. That was not the intention. I prefer to have some kind of wire connector, although these are solid wires, but if anything moves, I don't want it to crack right at the start. Same with the output. Or is that the output? Nope, that's the input. So input and output, both BNCs, and here we are. We've got, when all the switches are down, we've got the bypass active. So from there to there, we should get practically 0 ohms. Let's see if we do, because we know that all of them are bypassing. So do we get 0 ohms? Let's see. Yeah, that's pretty much 0 ohms. Now, as soon as I do that, we start getting a change. And it's not necessarily 75 ohms, obviously, because this relies on the impedance that's coming in and the one that's going out. But yeah, okay. So we've got our front panel done. All I did is I made those 4 holes on here. Put that on 0. I made the 4 holes on here. I did do something rather stupid, which I've got to warn you about. If you're going to put something like this on an enclosure, and you want to use the switches to hold the board down, there's one little bit of advice I can give you, which I did not follow here because I was stupid. And that is, you should put these switches in first. You should tighten them all, and then you fit the board on top and solder. I didn't do that. I actually soldered them in first and then put it through. It doesn't make that much difference, but what it will do is, if you do it the proper way, it will avoid any stress on your pins over here, because when you tighten these, you can sort of stress the board. Remember, these are solder joints. The board is now part of that, and you can create a bit of stress on the board, which is unnecessary. But yeah, okay. So, as I said before, this one is set for 10 dB, minus 10 dB. This one's for 20, and this is the 75 ohm, 300 ohm selector. And if you put it on 300 ohm, you get 11 dB of attenuation as well. This thing is direct coupled. In other words, there's no capacitor on here. So we do have to bear that in mind. If I want to use this for something else, I've got to remember that. I should remember it because the one that I did for the 50 ohm one, I mentioned that it's AC coupled, not direct coupled. And the reason I don't want to put a capacitor in here is that then goes and messes things up in terms of attenuation and in terms of impedance matching. So I leave it as it is. We'll see how we get along. Obviously I could still do it. All I need to do is remove one of those and put a cap on there. If the cap is big enough, it shouldn't affect anything, but I'll leave it like that for now. Anyway, this thing fits really nicely on here. I put this thing slightly off center. In other words, I put it more to the top so that the switches would be as close to the center as possible. Don't you like the labeling? Yeah, I could have done a faceplate and everything else, but I've got so used to doing these that I quite like it. I quite like sort of the homemade rugged look. And now what I want to do is I'll put these on, and these enclosures have very good fit. You seal it pretty well, and then I'm going to test it, and I'll probably test it with a normal signal generator. I've got to be careful because that one is a 50 ohm output impedance, so I've got to see how I can guarantee that the readings will tell me what I want to know. And then I'm going to see what these various attenuations do. See if we've got something that works. Because remember, this is not specifically built for FM. I'm going to use it for that, to break this down or bring this down. But it's not made for FM. It's just made for these are resistors. So effectively, the impedance of a resistor is not frequency dependent. However, what is frequency dependent is the inductances that the leads have, the parasitic capacitance that you might get on the board, or even component to component. So as you get higher in frequencies, some strange things might start to happen. But I will know the first time I use it to align a radio. But anyway, let me show you this thing working with fairly low frequencies, 20 megahertz, which is the limit of my signal generator here, and we'll see on the scope, see what it is that we actually get. What I've done is, because I've got a 50 ohm signal generator, I'm going to monitor the input and adjust the signal level on the scope based on the actual value that I'm reading there. And then I've got a 250 ohm resistors in parallel. So this is 75 ohms across the output, just tacked in there, so we've got a proper 75 ohm termination, because my scope is, 11 meg as it is, because it's in times 10. And we'll see what it is that we are going to get. So 20 megahertz signal coming in. Let's see what the scope gives us. Okay, here we go. I've got the input signal, which is the yellow, and the output signal, which is the violet, and I'm going to switch on the signal generator. 20 megahertz. What are we seeing here? 116, 118. So they are practically sitting one on top of each other, one on top of the other. Now, if I switch on 10 dB, okay, what have we got? We've got 37 millivolts output for 120 input. Now remember, that's changed because of the impedance that's come in when I've switched that on. So what I'm interested in is to make sure that the input level, it's input level, actual input level versus output level. Okay, so let's see how many dBs that is. Okay, now we'll deactivate the 10 dB and we'll activate 20 dB. So now we're sitting with, what is this one? It's 121 in and about 12 millivolts out. Okay, let's deactivate that one, activate that one. Same thing, 120, 121 in, 12 out. Okay. Now the problem if I try to sum these is that guy gets so small that it's difficult to determine whether it's reading something or just the noise sort of overshadows it. But it looks like 121 in, 5 out. What if I do this? What if I increase that significantly? Okay, yeah, that's better. That is 620 in and 18.5 out. Okay, we'll see. We'll do the sums and see what that comes out to. Now, let me take that off. I've got to bring that down. Still got 10 dB on there. Okay, they're back to equal. The signal level is just a bit higher, so it's easier to measure. Now, if I activate the 300 ohm, everything goes haywire for two reasons. One, I've got 75 ohm, it's reading 75 ohms output impedance, so it's not going to give me a decent value. I've actually got 75, it's expecting 300. But nevertheless, just for reference, we've got 588 in and 133 out. What I'd need to do is I'd need to actually put a 300 ohm resistor on there, and I know it works, so I'm not going to do that. But that is the result. That is the result. And now I know that I can simply sum them. I can bring the signal in at 75 ohms. I can attenuate by 10 dB, attenuate by 20. If I've got the two together, I end up with 30. Wrong. That would be 10. That would be 20. That would be 30. That's 40. 50. And if it's on 75, that's 61. Okay. That's our little device done. Now all I need to do is get rid of the probes. I'm going to remove that resistor here that was just tacked on temporarily and cover it up, and we're done. And that's it, folks. It's done. Now, is this thing perfect? No. Is this thing going to work for me? Yes. Why? Because I am not that much of a perfectionist. I don't require absolutely accurate readings. I don't need to know exactly how many dBs it's going in at. Most of the time, the alignments I do not require that kind of precision. If you are dealing with some of the stereo receivers, from the 80s, things like X-Ray Tony uses or does, I guess perhaps then you'd want something a little bit more precise so that you can test for sensitivity and everything else. In my case, no, I don't need that. These radios that I do I do them as a hobby. When I do want to align them, I want to be able to reduce it to the point where actually by ear I know that it's right. In other words, if you're doing an alignment and you don't want the AGC to kick in, you've got to reduce the amplitude, for example, okay? You wouldn't be really doing an RF alignment worried about the AGC, but that's just an example. Whether it's an exact reading or not makes no difference. I never look, or I've never done an alignment that uses those sensitivity measurements. If you remember the last one I did, I told you I'm not going to mess with this. This was the Grunich Satellite 3400, which I'm still waiting for parts on, but I don't really worry about that. It's not something I need. I know whether it's receiving well enough or not for my needs. I've got a feel, basically because of where I am, of how sensitive this thing is or not, because I use sort of a comparative measure of performance between the various receivers that I've done. So this thing is going to work for me, and I can now I've got to throw that one away. I'm going to share this on the PCBWay website. As I mentioned, if you want to get boards, you can order directly from there. I have not found anything wrong with the boards, my design of the boards. Usually that sometimes happens, but this version actually has come out very, very well. I want to thank you for watching. Thank you for your patience. If you like this video, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon. Links at the end of the video and in the description below. Thanks for watching. Bye for now and stay safe.